Okay, we're back. This is Clinton Weir discussing the my final project for CSC 535 Deep Learning at University of Illinois in Springfield for the spring semester of 2024. In the last video, I discussed the display confusion matrices code block. This is used to give little more detailed information than just accuracy. This shows for each class, for each label, for each classification, it shows how your predicted and actual labels compared. So you have 100 discus locks, maybe 90 of them were predicted to be discus locks, maybe 5 of them were predicted to be unlocked, whatever. And so it gives you more detail about the performance of your model, confusion matrix. And then I discussed using a heat map to improve the visual quality of your improve the to improve the presentation. Yeah, that's the word, the presentation. So moving on. Now, we talked at some length about the layers in your model. That you have different layers. We're using a convolutional neural network to classify these images. The reason, especially, is because an image is a grid-like structure. It's a grid-like data structure. It's got it's got rows and columns of data. It has each position in the grid has 3 values. Associated with red, green, and blue, I believe, but 3 different color values. And when you combine those 3 color values, you get the color that you observe. But the important thing is that an image is grid-like. So that's why we want to use a two-dimensional convolutional. You want to use two-dimensional convolutional layers. And each, it's nice. So the convolutional layers are based on the idea of a filter, and each filter is associated, with a kernel. A kernel is a grid. It's a square. Well, I don't think it has to be a square necessarily, but it's a grid of weight values, and so it just runs across. It runs across and up and down your image, and it's kind of like that game, Conway's Game of Life. It applies to a block, a square, rectangle, whatever, of the image. It applies so each cell, each pixel has a value, like I was getting into saying. It has a numeric float value. So each kernel has a square or rectangle of float values. At each position, it gets a little more complicated than what I'm saying, but at each position in your image, this kernel, is multiplied. You multiply the pixels that are in relative positions relative to your pixel that you're interested. You multiply that float value in the kernel by that float value in the image to get what I believe they call a feature map. And then you just, like I said, you just run that from left to right on your image, and then you move down to the next column, the next row, run it across, run it, row by row, and you get something. You get a grid of values. So that's how these filters. Each filter has a different kernel. Each filter is associated with a kernel. And then each filter has the capacity to detect each filter has the capacity to detect a certain pattern. I think this is basically what it does. It detects a certain pattern, and conceivably maybe it could detect more than one pattern. Could be used. I'm not sure. I'm a little fuzzy on that now that I think about it. But so you have multiple filters that they detect different things. Okay, so the convo layer, convo block, uses batch normalization, which is a regularization. I think is what it's for. Is to reduce the risk of overfitting. I think that's what it's for. I know we always used the batch we always used a batch normalization layer and ReLU activation. It's just so it's just so ingrained. I didn't even question it. But so the ReLU squeezes the output of the layer into -1 to 1. It squeezes, it's definitely used to prevent exploding. I think they call it exploding gradients, but it squeezes values into the range that we want. Okay, and then the next function is really just there. This code could be in the model builder that we'll look at later, but I went ahead and by putting this multiple block code here, then it will make the code later a little cleaner. I think the model builder code will be a little bit cleaner because I put this here instead of down there. So what this does, Number one, it creates multiple convolutional filters, convolutional layers, and this is, so it stacks them. It stacks multiple convolutional layers. It has an argument for the number of filters in the first convolutional layer, and it keeps track of how many, there's an argument that's passed to say how many convolutional layers we want. So as a rule, I am doubling the number of filters for each subsequent layer, each subsequent convolutional layer. So by default, the argument is passed. The first layer will have 16 filters, and then the next one would have 32 and 64 and so on. That's just, I think it's a good convention, but that's the convention I am using. And it's enforced right here. I don't have to think about it in my model builder. I don't have to enforce it down there. It's enforced right here while I'm thinking about it. Then this max pooling smooths out, if I recall, it smooths out the feature map. There's a couple different options for doing so, but it takes the average over an area of the image of the feature map. Sorry. So that's that. It's just code to do multiple convolutional layers, just to stack multiple of them. That's pretty straightforward. Residual layer uses separable. This is the analog of a convolutional layer, except it's using separable convolutional layers, and so it's basically the same idea. It still uses batch normalization and ReLU activation. Residual block I don't think this residual layer is even used. That's an oversight. So the residual layer is what it's called. It should probably not be called that, but uses a separable convolutional layer with batch normalization and reload. Okay, and then let's move on to a residual block. Obviously, I had in mind to use residual layers rather than convolutional layers. And at some point, I changed my mind on that and didn't make all the necessary, didn't change some of these function names. So this residual block, the primary thing here, it's right here. The primary idea, the primary purpose is this highlighted line of code. The residual block receives a signal and transforms that signal using two convolutional layers and a max pooling layer. And so after you have a signal, after you pass through these layers, you get a signal out, and sometimes the signal that you've got back out of these layers, the output signal has vanished, I think is what they call it. It's, so you've lost your signal. It's gone to zero. So a residual block, in anticipation of that happening, the residual block allows you to short circuit around these layers. And that's what this does. It adds the input to, the input of the block to the output of the layer. And that way, if the signal vanishes, you don't lose it. Now, something I thought about, and maybe I will try this out, is what if instead of using the, instead of adding the two signals, the input signal and from the previous layer and adding it to the output of these layers inside the block, what if we used just max of the input and the output? Just use the max. I don't know how big of a, how that might, I don't know what the implications might be. That's why maybe if I had more time, I would have played around with that. But my motivation primarily would be, would this shave off a little bit of time, and or would it shave some computation time? Would it make the process a little bit more efficient? I'm not convinced it would. I'm not convinced. I think computers are just really, really good at adding numbers. They aren't necessarily, I'm not convinced they're necessarily that much better at comparing numbers. So, so that motivation may be, may not justify this kind of a change. I'd have to think a lot harder on whether I'd have to think a lot harder about what the implications might be, and why we might be discouraged from, why adding might be the right choice. So then I have this residual blocks thing here. From our lessons, you want to use an ordinary convolutional layer before you do a residual block. That's what we, that was the lesson. I'll have to review, because off the top of my head I don't recall the specifics of that lesson. We're still using our filter count. We're still doubling. We're still going to double between layers, sorry. Okay, so we double the filter count between layers. So I have a bit of code here. So one of the things that I ran into while doing this project, I at a point I tuned the number of layers, and the number of filters as well. To tune the number of convolutional layers that I want in my network. I tune that value. I end up with 4, but we'll get there. Well, not in this video. This video is not so much about the results, but 4. So, like I said, we need to have a convolutional layer, not just not a residual block, just a convolutional layer. We need to have it at the start of our, toward the start of our network, before we do any residual blocks. That's what the lesson was, and I'm sticking with for now. But you could want, so if you want, we want to tune the total number of convolutional layers. And if you tune that number, if you want that number to be even, well, you can't get there with an odd number plus an even number, if that makes sense. Because the residual block contains 2 convolutional layers. So all that is to say that if I pass an even number of layers, then I'm going to do 2 convolutional layers instead of 1. So that's what this is. Start index is 1. If the total layer count is even, then I'm gonna do another. I probably could have done that a little tighter. Okay, so I could probably do X convo blocks. This is what I want. I'm going to leave this alone for now. I'm not sure if I want max pooling. I think I did this. I may have done this wrong. I might want max pooling after this ReLU layer. So that's what I did here. A convolutional layer and then a max pooling layer. I'm gonna come. So I might need to make a change, but just to show you real quick. So I would do if layer count is even, then do 2. Else X equals convo block. I don't know why I didn't do something like this already. And then I'd have like a filter count equals the first filter count And if I'm doing 2 layers, then I would multiply this by 4. So the first layer, would I multiply it by 4? Yeah, because if this was one layer, then I'd multiply it by 2, and because it's 2 layers, multiply it by 4. And then I'd have this down here. And then after that, I would have this block. Start index equals 1. Start, what is that? Okay, so layer count is 2, then start index will be 2. And this is right, because if you're doing your residual block is 2 layers, and so after each block you double the filter count twice. So this is, I think, what I would need to update the code to. And this is a lot tidier. So I don't know why I rewrote the convolutional layer right here. I'll need to revisit that. But in any case, let's move on. Data augmentation. So this, I think I may have talked about this already, but you can each image that goes into your model, into your CNN, each time that an image goes in, it will be. Now, let me backtrack. Okay. So, depending on the configuration of the model, it'll either use convolutional blocks or residual blocks. Well, it'll either use convolutional blocks. Yeah, that's fine. But when you're using residual blocks, you will have 1 or 2 convolutional layers before your residual block begins. That's depending on the configuration of the model. And this is also dependent on the configuration of the model. And some of the specifics will also depend on the configuration of the model. So data augmentation will or will not be used depending on the configuration of the model. If it is used, though, then it will apply a random zoom, up to, depending on the factor, I think I use 0.2, plus or minus 0.2 out of a possible 1.0. I think 1.0 is the limit. So it can be, it'll randomly zoom, brighten or darken, and increase or decrease contrast of the image. I did not choose to use flipping. I just all of the latches that we look at are going to be they're going to be left to right. The latch, we're going to take the images to where the lock side of the latch is on the right, and the latches all pretty much look the same. So they're not going to be flipped left right. They're not going to be flipped up down. Maybe you could make an argument for flipping them up down, flipping the latches up down, because they have vertical, they have symmetry. They have vertical symmetry. I think. Let's go back and look at the random images for a moment. So you can kind of see left, right, or right, horizontal, vertical. Gosh, I just cannot talk. If you flipped the image horizontally, left, right, then these slots would be over here, and this latching mechanism would be over here. And that's just never going, we're never going to find an image. We're never going to produce an image where the latch is flipped horizontally. Now, technically speaking, we will never see an image where the latch is inverted vertically. However, the latch is symmetric to a vertical flip. It's symmetric. So and it's possible, let's just think about any one of these images. If you flipped it horizontally, some of them would be a little funny. Like, imagine like some of these padlocks. You expect that the weight would cause the padlock to hang from the latch. Think it would hang from the latch. You would not think that it would, the heavy side would be up. But it's not impossible. I've seen it. I've seen padlocks where the heavy side is up. I think because the loop is tight around is tight on the latch, and so yeah, I'm gonna do it. I'm gonna do, maybe not right now, but layers. Yeah, I don't know the exact flip vertical. So you can randomly invert an image vertically, and I think that makes sense. But flipping it horizontally just does not, because you got your latch, the lock side is on the right, the sliding mechanism is on the left, and that's, if you flipped it horizontally, that's an image we are never going to see in the in the testing set, or in the real world data, in unseen pictures. We're only the only way we'll ever see one of these images horizontally flipped is if we artificially create that image. So I don't, it doesn't belong in the training set. Vertical flip, yeah, you might see some images in the training set where you could find images in the testing set where it is vertical from in which it looks like a vertically flipped image from the training set. Any of the training images, if they were flipped vertically, could resemble an image you could see in a testing set. I don't know, I think I'm explaining this well enough, but a vertical flip makes sense. A zoom, we have images at different levels of zoom. That makes sense. Even if it even makes sense if it would even make sense if the latch does not appear. If parts of the latch are cut off in the image, that could happen. If it's zoomed out, further than what we did in the training set, if it was, it's possible that that image could be zoomed out from that. Brightness, maybe we'll have images taken with a flash, so there could be a dramatically brighter image that we need to identify to the lock on it, and there could be times when the light, it's dark. When it's darker than the images in our training set. Could the contrast? I don't have a good example for that, but it's possible that images could have more or less contrast. So these 4 transformations make sense. But yeah, so images from the training set will go through this filter. They will be randomly adjusted in these various ways. And this will have the effect of simulating a larger data set than what we actually have. So that's the purpose of the data augmentation layer. So that's model component definition. Those are various kinds of layers that we will see in the model builder, which will be covered in the next video.